Welcome back. Now I'm going to invite Dr. Tuba Tata to introduce our next speaker. Please, Professor Tuba.
Thank you, Dr. Masquita. Welcome back, everyone. We continue our conference with next speaker, Professor Dr. Alper ILKI. His speech title is Seismic Behavior of Damage and Repair Reinforced Concrete Members. Before we start his presentation, I would like to briefly talk about his career. Professor ILKI is a professor of structural engineering at Istanbul Technical University. His research interests include the structural behavior of reinforced concrete and masonry structures, particularly the historical ones. The other main fields of his research interests are large-scale structural testing and structural seismic retrofitting, particularly through innovative techniques and materials. He has worked in the restoration of a large number of historical structures in a wide range from bridges to towers, from mosques to churches, including Hagia Sophia in Istanbul, Hagia Sophia in Lefkoşa, Edirne Selimiye Mosque, and Sivas Divri Ulu Cami and Hospital, among many others. He is associate editor or editorial board member of ASC Journal, Structural Engineer, ASCE Journal of Composite Structures for Structures, Arabian Journal for Science and Engineers, Bulletin of New Zealand Society of Earthquake Engineering. He co-edited 3 international books published by Springer titled Seismic Risk Assessment and Retrofitting, Seismic Evaluation and Rehabilitation of Structures, and Advances in Assessment and Modeling of Earthquake Loss. Dr. ILKI is an elected member of IIFC Council, head of Turkish delegation to FIB, chairman of board of direction of Turkish Earthquake Foundation, and a member of board of Turkish Catastrophe Pool. He co-chaired the organization committees of Smart Monitoring, Assessment and Rehabilitation of Structures International Conference Series in 2013, 2015, 2017, 19, and 2022, and the 10th International Conference on FRP Composite in Civil Engineering, the official conference IIFC, among many others. Professor ILKI, it's a pleasure having you here. Thank you so much, and the floor is yours.
Thanks a lot, Professor Tatar, for the very kind introduction. I think I should do something, or? Okay. Thank you. First of all, I would like to thank a lot to the organizers for inviting me to this important international event. I'm happy to be a part of this. Today's title is Seismic Behavior of Damaged and Repaired Reinforced Concrete Members, which is actually a very, very difficult topic. So you may feel that this will be a kind of brainstorming rather than sharing everything with you, because still we have many unknowns on all these issues. So as I said, it will be a kind of brainstorming to discuss some issues with you among colleagues. So the other authors are Dr. Demir, Bilal Sarı, Ömer Faruk Alıcı, and Şener Kölemenoğlu. They are PhD candidates. They helped me for the preparation of the presentation files. Let me go ahead. This is the content. After a brief introduction, I will talk about seismic behavior of reinforced concrete members, main characteristics, as well as damaged reinforced concrete members. And then I'm going to talk on the national damage assessment algorithm. Actually, this is on the way. Currently, it is used by Turkish Catastrophe Insurance Pool, which is an obligatory insurance system which very well works until now. This was established after 1999 Kocaeli earthquake. So all the countries somehow insured in terms of seismic risk, which makes a great pool of sources which can be used after an earthquake that may hit anywhere in Turkey. It's one of the largest insurance pools in the world, if not the largest. Then we are going to talk a bit on the seismic behavior of repaired and retrofitted reinforced concrete members. And then I'm going to summarize an ongoing research project which targets to establish a new seismic design performance level, which is called as repairable damage, which came to our terminology after particularly the earthquakes that has been exposure after Christchurch earthquakes in New Zealand. And then I will finish with conclusions. So, as all of you know very well, capacity design approach is now being used all around the world in seismic design, which is, of course, very effective in preventing loss of life. That's very good. And because of previous structures which have not been built considering the capacity design principles, such as strong column, weak beam, and the strength hierarchy in terms of flexure and shear, and so on, we had many casualties actually due to unpreferred failure mechanisms of the structures. But hopefully, after these capacity design principles have taken its place in the seismic design codes, hopefully these kind of life losses will be less. So it's a kind of key component now in all the modern seismic design codes, which basically adjusts somehow the locations and types of inelastic deformations so that we can avoid total collapse of the structure, although the structure dissipates a lot of energy, experiences a lot of damages, while standing still against seismic actions without a substantial loss in strength. So this graph shows you a kind of conforming type of behavior with the green curve and the non-conforming structures with the orange curve, I would say. These are load displaced, schematical load displacement diagrams. And what I would say actually, and unfortunately, many structures in Turkey have been built in a kind of non-conforming way. Therefore, unfortunately, after every earthquake, we experience some kind of this orange curve-like behavior in many structures. And so something must be done. And in other words, we will have a lot of damaged structures after potential severe earthquakes, which where the repairing and sometimes retrofitting will be unavailable. So that's the issue. Seismic behavior, seismic retrofit and repair are very, very important issues, not only in terms of new buildings, which will also be damaged during a strong earthquake, but also for existing structures which have been constructed in a non-conforming way. And yeah, that's good, the capacity design principles, but unfortunately, this kind of design strategy does not guarantee that the structures will be usable after the earthquakes, and they neither guarantees that those buildings will be repairable after the earthquake, as clearly demonstrated by the Tohoku earthquake in Japan, with a photo on the left-hand side, and also another damage in Christchurch in 2011. Of course, there are many more examples. So that's the main philosophy of current design strategy, where we rely on damage, plastic deformation, ductility, which sometimes there's no way back other than demolish and reconstruct new buildings. So that's not very good in terms of cost, financial cost, but also time, a lot of social problems because of necessity of finding some living places for many people, and also not good for the environment because the demolishing parts should be stored somewhere, and also we need new materials from nature. So it is good if we can build some buildings which can be repaired after they experience damage. In terms of financial aspects, the Christchurch earthquakes, after the Christchurch earthquakes, more than 60% of the multi-story reinforced concrete buildings should have been demolished and reconstructed. That's a huge cost, even for rich countries. But I mean, that's quite unbearable cost for countries like Turkey and similar countries. So a change on our mindset could be necessary to avoid such losses after large earthquakes. In case of Turkey, I mean, all the other cities are somehow manageable. But if the earthquake hits Istanbul city, which is in a very high risk of earthquake, then since most of sources are already in Istanbul, the situation would be very critical. as shown clearly with also previous photos, the code-compliant buildings may also suffer very heavy damage, as you see on the figure right bottom, which makes the use of building after the earthquake impossible. So although these buildings were designed according to capacity design principles with today's strategy, that's not the best performance we would expect after an earthquake nowadays, actually. So if you look at general characteristics of seismic behavior of reinforced concrete members, as all of you know very well, the cyclic behavior is basically represented by a kind of stiffness reduction. So that's how we can model the damage actually, as well as a reduction in strength, which are based on the normal force on the member, the reinforcement details, and so on. So, of course, these at the end come up with a reduction in displacement capacity, ductility, and consequently energy dissipation of the structural systems. Therefore, for interpreting the seismic behavior after an earthquake against the next earthquake, we have to know the consequence of damages very well, and we have to know how the repair methods will affect the performance of structure against the new earthquake. Of course, that's a very difficult topic, and there is not too much research on these because there are different types of damages, different extents, different types of members. So a lot of research, I believe, is needed for that because there are cracks which are flexural or shear, concrete crushings, cover spallings, reinforcement bucklings to different extents, as well as core crushings, which all necessitate some different interventions. And although there are a lot of research on seismic engineering, on columns, beams, joints, full-scale structures, unfortunately, most of the time, the residual state is not reported very detailedly. So generally, we have the deformations, damages at the maximum load, maximum displacement, but the ultimate situation where the system is totally unloaded, which actually represents the situation after an earthquake. That's the state. What we see on site after the earthquake is less reported, which is actually very important to connect what happened at the maximum displacement and what happened at the after the earthquake. There's little information on that. And also we have to pay attention that although the code-compliant reinforced concrete members may show a gradual damage development, hopefully, but non-conforming members can fail very rapidly. One example, I will show here a video which is kind of very representative, a column of many structures available in Turkey, particularly in Izmir in 2020. Many structures have been collapsed. Mostly those buildings had columns similar to this one. Let me show you the video. I said that the column will fail at the drift of 0.5%, which is much less than what you would expect according to design rules. So the column is being pushed or pulled. Anyway, we have a vertical load on the column, and that's how it fails, like a total destruction because of high axial load on it, and very, very rapidly. Let me go ahead. Another problem is the damage and the extent of the degradation in strength may not be visible after the earthquake due to some damages which we are not used to see. I mean, the code compiled structures behave and get damages as we expect theoretically, but because of some details, because of some plain bars and so on, insufficient anchorages, there are many different failure mechanisms. And maybe I can show you one video here on a project that we have conducted several years back on site. So you can see the building while it's being tested on the middle. I don't know if it works or not. Possibly works. Yeah, it's working. So the test has gone up to 4% drift, as you see on the graph on the left-hand side. And at 4% drift, the strength reduction was about 40%. Okay, that's good for the structure because it's beyond our expectations. I mean, we wouldn't expect the structure would go to 4% drift and still stand. It went. And more interestingly, the damages was very slight. We didn't see much damage on the structure. And when we analyzed this, what we saw was that the failure mechanism is totally a mechanism which is never considered in design, because it was totally due to slip of longitudinal bars. So the longitudinal bars were slipped, debonded from concrete all along the lap length, and the bars were just moving like a tension ties from the footing to the end of the hook. So the plastic, I could say, very little amount of plastic deformations were accumulated along this embedment length, which was much higher with respect to potential plastic hinge length on that column. Therefore, the unit deformations all along the lap length was very limited, so that the damage you could see on the site when you go there was much less with respect to the damage that you would expect from that kind of non-compliant structure, which has been subject to the drifts of 4%. So this makes our work difficult. Another video, at that time, I have to speak about 45 minutes. So to make you awake, I have to show some videos, etc. And that's one of them. We have made some tests on full-scale structures several years back. These are actually not specimens. They are, full-scale buildings. And the left one is tested as is. They are identical buildings. And the right one has been tested after retrofitting the first two-story columns with FRP confinement. I'm going to trying to show you how the failure mechanisms change before retrofitting and after retrofitting. The left building collapsed at about 1% lateral drift ratio. As you will see in coming seconds, you will see some slow motions and more close-up views of how the columns have failed. Actually, these are not the worst type of structures available in Turkey. Their concrete quality is higher than average. Their transverse bars are like that. The vertical loads on the columns are not as high as many buildings around, but still the displacement capacity was just 1%. Look at the column closer to us. When the increase of lateral forces and little bit displacement at about 1% at first story level, the columns crash because of insufficient transverse reinforcement, and that's the mechanism. And here on the left side column to the front, you will see a shear failure mechanism because again of insufficient transverse reinforcing bars. You see a closer up view here. Yeah, if we had these transverse bars there, we would avoid such kind of failure. Then what happened to the building retrofitted? While this building collapsed at 1%, the building survived until 15%. You are not hearing wrong, 15%, 5%, which makes 45 centimeters lateral displacement at the story level, in the first story level. So the excavator machines are just there for security measures. They are not touching the building because the systems are there. So after 15% drift, this retrofitted structure hasn't collapsed. So we had to collapse them by the help of these machines after the end of the test. There are other tests which I will not show due to sake of time. In eDefense, we have some joint projects going on with them. And so in each test, based on the design philosophy of the structural system, we come up with different failure mechanisms, which would require different repair methodologies. So how to determine the seismic performance of earthquake-damaged RC buildings? That's important to determine what kind of measure we are going to take. Shall we repair or shall we retrofit, or what kind of repair we are going to conduct? And of course, this depends on the level of damage, either heavy damage or moderate damage on some members. There are some documents, some guidelines for that, like the FEMA 306, like the Japan Building Disaster Prevention Association guidelines for post-earthquake damage evaluation and rehabilitation. As Turkish Catastrophe Pool, we have a post-earthquake damage assessment methodology. It was there since 2003 or something like that, but then it has been revised recently. And it's nowadays the Minister of Interior, the AFAD, and the Minister of Environmental and Construction discusses to make this a kind of national damage assessment methodology, which would be good because nowadays different institutions conduct different damage assessments, and then different results can occur, and this is not very good for the people. Also, there's rather a global damage assessment scale, European macroseismic scale, and also Italians have this document for determining post-earthquake damage and safety, as well as recommending some short-term measures. If you look at FEMA 306, which gives quite detailed approaches to tell us how we can consider the effects of damages on our structures for modeling the building after damage. Basically, there are three parameters, one of which is the modeling of stiffness of the structural member. The second one is about strength. And the last one, which is just seen here, gamma D, is about the displacement capacity of the structure. So it is very good that based on the level of damage, for example, slight damage and moderate damage, the document gives us how to consider the reductions in displacement capacity, strength, as well as stiffness. And better than that, the document gives us how we can model the structures after repairing with different techniques. So that's quite a good approach that could be used to assess how the damaged buildings, how the damaged members behave in the next earthquake, either before repairing or after repairing. And we have used that while we were developing the Turkish catastrophe pool damage assessment criteria. Another similar one, not exactly the same, is the Japanese document, which is based on the lost energy dissipation capacity during the earthquake divided by total energy dissipation capacity. So with this one coefficient, while FEMA document considers stiffness, strength, and displacement capacity reductions with different coefficients, the Japanese use just single coefficient, which goes from 0 to 0.95, considering the type of the member, shear wall, beam, and column, as well as the degree of the damage. So with those, you can estimate how much more residual seismic performance you have in a general sense in terms of remaining energy dissipation capacity. And Turkish catastrophe insurance pool disaster, damage assessment methodology, which was lastly developed, revised in 2020. There are two inspection procedures now I'm going to share with you, but actually there are three. The one that I don't show here is for very critical situations, like very crisis situations. I mean, you have to be very, very quick to make the assessments. Then we have a simpler algorithm. In case we need to be more quick, then these two methodologies allow us. And these two methods are for relatively smaller structures and larger structures, I would say. And for smaller structures like plan area less than 600 meters square and number of stories less than 10, all the damage of vertical and horizontal members are taken into account because since 1998, capacity design principles are in place in Turkey. So we expect that the buildings constructed in the last 20, 23 years, 24 years will fail due to the damages of horizontal members rather than vertical members. So they are included as well. And the damage thresholds, definitions of different damages from 0 to D, from none to very heavy damage, is kind of calibrated from test results. Many tests have been considered in literature, including our own tests, and then these limits were put, which are quite in agreement with the other damage assessment methodologies. And then many, I will explain, I think, in coming slides more. We conducted many nonlinear analyses on different structures with different geometries, different structural systems, and different estimated damages. And then we determined what should be the slight damage in terms of structural scale, what should be heavy damage, and what should be the moderate damage. And basically, the main idea of slight damage is the loss of about 10% of seismic capacity of the structure. So the structure should resist at least 90% of initial capacity without damage. Then that's slightly damaged. And 10% is the highest. Probably it's much less. And heavily damaged buildings are decided based on the financial cost, because there are some heavily damaged members, moderate damaged members, and if the repair of this structure, including non-structural damages, column damages, beam damages as well, if it's over 40% of the new construction, then that's designed and heavily damaged. And I will explain how we made these calculations, how we come up with these ratios. So in that case, it's enough for us to deal with the number of damaged members. So based on the number of and the degree of damage of vertical structural members and that of horizontal members, we decide whether the building is moderately or heavily or slightly damaged. Due to sake of time, I'm not going into details. The more detailed procedure, which we suggest to be used for larger structures or higher structures, is with a weighted damage percentage of vertical members, and also based on number and types of damages of horizontal members. So that takes more time on site to apply. The basic philosophy are same. Very limited amount of loss in the seismic capacity for slight damage, and financial considerations for deciding whether the repair is feasible or not with respect to demolishing and new construction. European macroseismic scale is, as you know, more global. Information is given there. AIDES, Italian's approach, has some questions about the damages and the extent of those damages, and then they can decide about the overall damage. So there are some research works on the change of stiffness and others. One of them is shown here. As a function of the achieved ductility, the stiffness of the structure is changed. Of course, there is a small scatter, which is very normal. But the good thing is maybe that after a certain amount of ductility, it becomes more asymptotic. So the deviation is not much, particularly for higher levels of ductility. And similar studies have been done for residual deformations, which of course at the end will affect our displacement capacity during the next earthquake. And obviously the residual damages also increases with the increase in the first earthquake, which has been represented by this kind of curve by Marco Di Ludovico and his friends. And of course, there are some empirical formulations, other suggestions for the reduction of strength and deformation capacity, but it depends on many things. Of course, like the structural characteristics, normal force, and the reinforcing bars, concrete, and so on, many detailing of reinforcement and else, but also more difficult things like loading type and rate. What I mean is that for the very same column, typically we make some uniaxial test on site, which gives sometimes good results, like you see on the left-hand side. But for the very same column, if you apply biaxial loading, for example, from Portugal colleagues, I guess, this study, the behavior could be remarkably different, which is many times not properly taken into account. And also the loading rate I have mentioned that could affect the behavior to a certain extent. Here, just an example from Marja and others. If you do a static quadratic test, and if you do a same loading pattern through a dynamic way, the displacement capacity and the strength degradation characteristics, as well as the pinching characteristics, are changed, as you see here. And also there are conflicting results, actually. There are some other tests which show this doesn't have too much influence. That's, of course, based on the characteristics of structure, failure mechanisms, damage development mechanisms. So it's very difficult because all members have their own characteristics, which makes it difficult to come to an easy solution. So seismic behavior of damaged RC members have been investigated by several colleagues, as you see here. I have mentioned already about FIMA, which gives us plastic hinge modification factors, but that's basically for shear walls and coupling beams. Maeda and others has given some seismic reduction factors for reinforced concrete beams as a function of the damage level. Ludovico et al. Has given some, again, plastic hinge modification factors for non-conforming RC columns, and Chu and others for conforming RC columns, and Marder and al. For RC beams. Where there are others, these are just some examples, but there's not too much. I mean, there's not a exact consensus on the behavior of damaged reinforced concrete members actually, and of course same is valid for repair, because the literature is very, very limited on these aspects. Due to sake of time, I think I should not spend much time on those. But anyway, Maeda and others has given the relationship for ductile and brittle members based on the concrete crack width, and that's the residual crack width, which you can see after the earthquake or after the test, as a function of damage class. They have provided the seismic capacity reduction factors, which I have mentioned that it's in the form of energy dissipation capacity. So based on the dissipation capacity reduction, you can decide whether this structure should be demolished or maybe repaired or not. As I mentioned, Ludovico has tested 18 non-conforming columns and have given some curves to take into account the change in stiffness as a function of this, the rotation ductility reached in terms of stiffness, ultimate load, and also the residual drifts, which can give us some hints to model this kind of members after damage during the next earthquake. And similarly, Chiu and others has tried to check the accuracy of the modification factors given in Japanese guidelines. They have tested 6 columns with different failure modes, flexural or flexural shear failure mechanisms, and they have shown that the energy dissipations can be more with respect to the Japanese guidelines. So they somehow this means that for some certain cases, certain characteristics of structural members, the guidelines may be unconservative sometimes. And also similarly, Marder and his friends has proposed a curve for the reduction in stiffness as a function of crack width on the beams. Of course, that's done for the support sections of the beams where is active during the seismic actions. And yeah, that's now we pass to development of Turkish national damage assessment algorithm, which is somehow quite similar to Japanese approach, considering the lost energy dissipation capacity with respect to the total energy dissipation capacity, where the damage modifiers for slight, moderate, heavy, and very heavy damage was also similar to Japanese guidelines, but then recently these coefficients has been changed based on a more deeper literature survey. So this means that a member with a damage level of A, which is slight damage, has lost 20% of its capacity, whereas for moderate damage, 0.4, 40%, for heavy, 0.7, and for very heavy, total capacity is lost. That's the assumption. And then, as I mentioned to you, based on the number or the weighted average of the damage of vertical structural members, the methodology allows you to determine the damage level of the structure. And nowadays, the Turkish catastrophe pool engineers use this approach automatically using some tablets during the damage assessment procedures. And that's a target for to make it in a more generally accepted methodology. And let's see how the slightly damaged limit is determined. I have mentioned this before. What we have done, we took into account several damage scenarios, which are realistic based on the post-earthquake damage observations after 1999 Kocaeli earthquake. And numerical models were prepared for the intact situations and damaged conditions of these structures, and pushover analyses were conducted for 200 plus cases. And then we just determined that what kind of damage distribution caused a 10% degradation in PGA capacity of those structures. So we said that, okay, of course, we also consider a confidence level of 99%. So we didn't work with the mean values, but we used with the mean values minus 2.5 standard deviation to be on the safe side. And that's what I mean. For rapid inspection, which I mentioned, that damage is defined based on the number of moderately damaged members divided by plan area of the building. And as you see here, this scale is not from 0 to 100, that's from 80% to 100%. And vertical axis is the relative PGA capacity of the damaged structure with respect to its capacity before the earthquake. So we said that, okay, 10% loss could be acceptable as slight damage. But when you add, of course, the 99% confidence level, this comes somewhere here, the red line, and you don't see any point below that. So it's quite safe. And we said that, okay, if we draw a line here, and if we say that the buildings with less than 10% capacity in PGA could be slightly damaged, then that's the value, 0.01. For the members, type B means moderate damage. The number of moderate damage divided by plan area should be less than 0.01. If this is fulfilled, your structure is slightly damaged based on rapid inspection. And if you go to detailed inspection, we did similar things, just we work with, rather than number of damaged members, we work with weighted damage percentage for vertical members, which is calculated with this kind of equation. Here, A, B, C, and D is the total cross-sectional area of members with damage level A, slight damage, total cross-sectional area of members with damage level B, C, and D. So that's a kind of weighted average considering the damage of each member and their cross-sectional areas. So, and then for heavy damage limit, what we did, as I mentioned, we considered the cost of repairs for structural damages and for non-structural damages. For non-structural damages, we didn't have much information. Actually, we have, but that we thought that it's better to stick with the what the literature says, because we have a lot of actually damages in Turkish catastrophe insurance pool, thousands of them. But it depends on the market condition and so on. So to be on the more scientific side, we use this relationship. We assume that the repair of non-structural elements plus mechanical, electrical, architectural details, it costs about double of the repair cost of structural elements after an earthquake. And with those assumptions, and also we got the market prices for column and beam repairs and shear walls and so on. And also we had to make an assumption about the distribution of damages from the ground story to the top. Of course, that's a very rough estimation, but you have to do something. And this changed from structure to structure remarkably, based on, again, a literature study, which also there are friends from Portugal as well. And also, depending on many earthquakes, like Elazığ earthquake, Kocaeli earthquake, we assume that, okay, if the ground story damage is like 1, and then the next story is 7.5, the next 5, and the next 2.5, and the damage above this could be negligible. Of course, that's not always correct. We very clearly know that, but that's an assumption we made, because in damage assessments, only the most heavily damaged story is taken into account. Therefore, we don't have data for the other stories. And I should say that even the data for the ground story is not very reliable, is not very objective. You can have significantly different decisions based on the person who is making the damage assessment and where he is making and what's the political situation on those days. So it's, rather approximate. We should accept that. And for determination of this heavy damage limit, we studied more than 80,000 damage scenario, and cost analyses were performed for different damages, keeping in mind that this is our limit. If the total repair cost, structural, non-structural, everything, divided by reconstruction cost, demolition and reconstruction cost, if this is larger than 40%, don't repair it, go and demolish it. These are important in terms of insurance sector to decide whether they will pay the full money or they will pay the repair money. So based on this, as you see here, for rapid inspection and detailed inspection, we determined what should be the damage level. This time, of course, we are looking for type C damage, heavy damage of the members, rather than moderate damages, because we are talking about demolishing of the structure. Again, if the number of type C heavily damaged members divided by plan area is larger than 0.15, then the repair cost exceeds 40% of the demolition and reconstruction. So that's the limit. If you are somewhere here, then you can repair. If you are somewhere here, you should demolish the structure. And same thing has been done for detailed inspection. Due to sake of time, I'm going to pass this slide without details. If there are some questions, I will try to answer. anytime, not during this presentation. Like, you can write me an email and I can try to answer afterwards as well. So then now we looked at the seismic behavior, we looked at the seismic behavior of damaged structures, and now let's see what we have in hand, how the structure will behave after repair. Of course, there are many works on quadratic tests, theoretical works, shake table tests, but they are generally singular and not too much covering everything. Some of them are here. Again, due to sake of time, I am passing those. Generally, we get good results after repair. Either the strength is recovered, or sometimes better if the repairing is including some retrofitting as well. These are done on columns, on beam column joints. Several studies here tabulated. As you see, based on the initial damage and also based on the methodology of repair, you can get different results. I mean, you can recover the strength or not. Sometimes you can recover the deformation capacity, sometimes not, and so on. This is valid for beam column joints and for other members as well. Here, for example, you see how the damage of a beam at support affects its stiffness and deformation capacity, as well as how the repair contributes to the behavior quite successfully to bring it to original state, recover the strength and deformation characteristics. And the Marja and others have proposed some relationships, as I have shown you a curve before, for determination of second stiffness, basically for beams, support regions where they don't have axial load on it. So these points show those experimental works, and the dashed line is their limit. So it's successful in terms of beams, but they have checked only one column specimen. And as you see here, this advice is not valid for that single column specimen they have checked in their paper. And interestingly, of course, this is the horizontal axis is drift ratio. So, sorry, displacement ductility. So you see that the column has been subject to a displacement ductility of 4, which is quite excessive for a column. So based on the level of axial force and other details, this can be possible, of course. But of course, this is much changing if the level of axial load on the column is different. So for beams, also there are scattering results. For columns, there are some studies, but the effect of repair changes as a function of the axial load on the column, whether the axial load is still there during the repair on the column, or you somehow support the system or not, and how long, which part of the column you are repairing, you can come up with different results. Let's go ahead. These are some tests from my research group, 2014, by using some GFRC jacketing, by spraying on 2 non-conforming columns. You see that this repair technique, which is somehow improving the behavior of the columns. There are many tests like that, not on this one, but most repairs, particularly that are used with repair mortar and then some kind of jacketing, either with FRPs or other kind of materials, then you will see a significant increase in ductility, and generally the strength and stiffness are also recovered. There's again a study from Portuguese colleagues, just repairing of the members with columns with some welding, reinforcing bars. Obviously, as you see here, not only the original behavior was recovered, but slightly better performance has been achieved. That's often the case, as I said, in the literature. So just some few words about our ongoing project, which targets to determine what is the repairable damage level, how we can determine it. So basically, we are looking for a new seismic performance level, which will be better for future earthquakes with respect to targeting life safety. Of course, this should be somewhere in between immediate occupancy and life safety, because immediate occupancy would not be economically feasible. Probably the structure will be too strong and too costly. And if you go to life safety performance level, yes, that's economical, but then the repair issues and the accommodation issues and financial issues would not be very good after the earthquake. So in between these two, there should be a repairable damage target level we can find, which is both economical and technically feasible. But the difficult question is how, what is it, and how it will be determined. It's very difficult. And we have obviously some, if we pass the conclusions with 2 or 3 slides, we have some data, very good data, for residual behavior of damaged reinforced concrete members, but they are not enough to come up with some general solutions. We have some post-earthquake damage assessment methodologies, which we have to accept that they are quite approximate, give some idea, but not enough to propose some new performance tables. Therefore, the extent of damage for repairability needs to be investigated. Which damage, which type of damage, which extent damage is repairable? This is very important to set a new seismic performance level, a new one, which will, of course, bring a more limited use of ductility capacity, which we like very much, which we have been designing for many years. And of course, for answering the same question, we have to know that which repair technique contributes how to our damage structure. Therefore, we need to work on different repair techniques as well. And that's not only in terms of technical issues, but also it's important to know the cost of this repair. If it is too costly, it's meaningless to use it. So we have to also conduct some cost-benefit analysis to check which repair solution is feasible or rational to use. And another thing is, the sustainability is a very, very critical issue today in our days. So therefore, there are always new materials coming up, and they should come up. Some low carbon materials, bioresins, and some materials that makes use of recycled materials. There are few work on that, not too much, not common, not in the market yet, but research is going on that. So we have to check their performance as well. So with that, I finish. You can see some references here on the presentation. And of course, there are acknowledgements to different institutions, as well as many, many individuals who have contributed to the tests and the studies I have shown here. With that, I thank you. And I think I just talked 44 minutes. That's good enough. And I have 1 minute for question and answer at least. Thank you.
Thank you, Professor, for your fantastic presentation, for sharing your knowledge with us. We have a question here. The question is about how the cities could take advantage of the methodology for risk mitigation and the data on seismic or others natural hazards you present today, and especially in the case of Brazilian situation. Could you tell us your point of view about the main issue that should be overcome today for we have less impact of our buildings under natural hazards?
Yeah, of course, very good question and very difficult question at the same time. I may not be correct person to ask it specifically for Brazilian cities. Maybe, Professor, you can answer it more because you know the situation better in Brazil. But I think we have people from Turkey as well. In case of Turkey, unfortunately, the assessment studies show that a very big portion of existing structures which were built before year 2000 have sufficient, unbelievable insufficiency. They are very poor and they are subject to collapse during the next earthquake. So in Turkey, what definitely we should do, and some countries as well around us, like Cyprus and others, we have to quickly make assessments, which is also expensive. So we should find some rapid and cost-efficient ways to get the data of these buildings and to analyze them, to prioritize them, and then to take action again through the most convenient intervention methodology and to the ones which really need this retrofitting. Because if in Turkey, for example, if you consider all the buildings which do not fulfill the code requirements, the problem is so huge that you can't do anything. So prioritization is very, very critical. Correct prioritization is very critical. I guess this may be valid for Brasilia as well. But I mean, frankly, I don't know the situation of Brazilian buildings.
Professor, thank you so much for this valuable presentation. We do have another question from Mr. Cesar, and he's thanking you. And then he is asking, I would like to ask whether the component engineers and academics are doing the detailed seismic assessment after earthquake. I know that rapid seismic assessments were made by teams, including engineers who do not know what column and beams are.
Again, very good. and a very difficult question. Thank you to Mr. Cesar. Current situation. The officially responsibility is within the AFAD, but AFAD is a coordinating institution. AFAD, under AFAD, Minister of Environment and Urbanization and Climate Change is the real one who is doing the work. So the staff of Minister of Urbanization does it currently. They're civil engineers mostly, and recent several years, there are trainings to them. I mean, we have developed some trainings together with the ministry experts on these items, and then they get lectures several hours before they can make this examination on site. But nevertheless, of course, sometimes based on scale of the event, there are some unexperienced individuals could also be involved. Furthermore, Turkish catastrophe insurance pool also makes some damage assessments. They have special group of experts, again trained. So the probability of mistake is not very high. And if there's some problems, they consult to more experienced engineers in the TCIP group, Turkish Catastrophe Insurance Pool. And academics, sometimes, of course, always on the field, and often closely contacted with the institutions, administrative institutions. So, for example, for very important structures like governor building, like the hospital, state hospital there, often they request the help of the academicians. So academician groups go to those buildings and give some reports about whether the hospital can be used or not immediately, there is damage on the governor building or not, and so on. So I should say 3 typical things: ministry, TCIP, and academics also. But academics portion is very small, of course, very important ones. Other than that, if the event is too large, sometimes volunteers are involved. Volunteers generally through chambers, Chamber of Civil Engineers or Chamber of Architectures. They gather. This has been done in one earthquake before. But if the capacity of the official, persons are enough, they don't prefer to use volunteers because of very critical decisions should be objective and they have been trained and so on. So that's what I know on the field. Thanks for the question.
Thank you, Professor, for your time, and you were sharing with us with your valuable knowledge. So, and then everyone, that we are going to present our next speaker. Please stay tuned, and then we are going to be back. Thank you so much, Professor, again.
Thank you.